So in this video, I'm going to look at creating an allocator that I can use with Zig, a standard library type allocator, but one that is backed by the Uefi-OS, the Uefi underlying services. So a little word about that first. When we're starting up our Uefi application, when we get into our pub/func main here, we are in what's called pre-boot mode. And pre-boot mode means that there is an OS, it's the Uefi firmware OS. It has services, it has a driver model, it has access to, as we have seen before, things like writing text to the screen, and we can read from the file system, we can use keyboard, USB devices, etc. So it is a fully fledged, albeit very relatively basic, operating system, 64-bit operating system. So we can write a complete application in that operating system, and if you wanted to now switch into creating your own OS, then what you do is you exit this pre-boot state and you enter the OS state, which is where you have complete control over the system. And one of the things that happens when you do that is that the Uefi firmware boot services, or the services that are available, these OS services that are available to you, they no longer operate, they're no longer available. And just as a little quick example of what that looks like, you can see here in the code that I'm doing something called exit boot services here. Exit boot services is the call to the Uefi OS saying, I'm done with all the stuff that I needed from you, I'm ready to take over. You can basically unload and shut down, and after that we are on our own. And just to sort of illustrate that, I've added a little output here. I write, you won't see this, and actually as I'll demonstrate in a moment, you won't see this, because at this point the boot services have been shut down on an output string doesn't do anything anymore. So let me just quickly run it. Right, so you can see I'm going to go through this. This is to do with the allocator work that I'm going to talk about today. But you can see here that after exiting and halting, there is no, you won't see this, because at this point we have truly left boot services, we're on our own, output string doesn't do anything, and it's our job at this point, and this is where you would create all of the services, all of the device drivers, setups, everything that you do for your own OS. However, I'm not going to do that now, maybe in the future, but at the moment I'm going to stay in pre-boot and be a happy Uefi application. So you saw some extra output being printed there, if you've seen the previous videos. This, what I was doing here was I was using my allocator. So what I've created is a small, very simple allocator which has implemented the standard allocator interface, which is accessible here in the source. And I create one of those, and then I can call all the standard allocator functions. I can allocate some bytes. I've allocated 1025 bytes here. I fill it up with some stuff. I print out the address. I can free it as normal. I can use the align alloc call, in this case aligning it to the page size, which is 4K. And if, in fact, I can run it again, and just so that you can convince yourself. Right, so you can see it prints out the two allocation addresses. This first one, ordinary address. This one is, as you can see quite clearly, aligned to page size. So that's exactly what we want to achieve. And then I can free it all up, and that's it. So this is not, of course, a very exhaustive test, but it's just showing that I can use the standard Zig allocator functions backed by my system allocator. And that allocator is in turn using the boot services. The boot services in Uefi have a very basic allocator built into them. It can allocate pages and pools, and I'll show you how that works. So to start with, I've taken a lot of inspiration. Part of this journey is, of course, to learn how to write better Zig code, right? And so I take a lot of inspiration from the code that's written in the standard library. I take that as being the sort of the canon of how to write good code. I can see it's evolving. It's interesting. I think everyone who's working on the standard library and Zig itself is obviously also learning and finding new and better ways of expressing what they want to do. But for the time being, I've used Allocator, I've used heap.zig, mem.zig as inspiration for how to write this. So the code is probably relatively similar to what you'd find in those in terms of structure and underlying idea. I have two allocator functions that are used to populate the interface, the standard allocator interface. One is alloc and the other one is resize. Resize is only used for deletion here, so I only implement resize for a new size of 0. That's purely laziness on my part. When I need resize, I will implement that, but it's also very easy to implement the free functionality using the underlying boot services. So the way that I've created this allocator is very, very simple. When you allocate some memory, it allocates the memory you want, so the amount of memory you're asking for, and then it allocates a pre-chunk. And in that pre-chunk, just prior to the pointer that you get returned from the allocation call, it inserts the allocation header. The allocation header is a small structure which has a cookie. A cookie is this random, truly random number here. It has the size of the entire block, so the entire range of bytes here. And then it has a pointer to the base allocation, or the actual allocation. And of course we do that because when you return the pointer, because you have alignment needs, etc., that will be different from the actual pointer to the memory block we allocated using the boot services, so that when you later on free it, I need to be able to retrieve this header so that I can find where the actual memory block starts, so that I can actually delete it properly. That's a fairly common cliche for doing allocators. So the actual allocator itself, super simple, right? I adjust the size to your alignment needs and the size of the header. I need a bit of extra room. I call boot services allocate pool, which is the function that just allocates bytes. There are two. There are allocate pool and allocate pages. In this case, I will let the boot services do the arithmetic of determining how many pages that's going to be. I tag it as loaded data. So the Uefi manual 2.6, which is the one I'm following, and I presume this is not going to change in the near future, recommends that for pre-boot, for your Uefi application in pre-boot, you allocate memory and tag it as loader data. So that's just a standard. So I allocate this pool of memory. I check for error, which is there's probably a better way of doing this, but for now that's good enough. I align the actual pointer that I get back so that I get a pointer to an aligned position, which is in the little diagram here will be this return pointer here, so I'm adjusting that. It's great that all of this is built into the standard library. Then I take the adjusted pointer, which is this one here, and I subtract the size of the allocation header so that I get to the beginning of the allocation header here in my block of memory preceding the pointer that I'm going to return. And that's where I now punch in the values that I want to keep for later on when I call resize, i.e. free. So I put in the cookie, the actual pointer to the base of the block that was allocated, and the total size of bytes. Then I have some leftover debug information here, which I was just using to print out so that I could track this. Debugging is something I will attack next, because I want to be able to debug this properly. And I want to be able to do it on Windows, which might turn out to be somewhat of a challenge. And then I return a slice created from the adjusted pointer, so the pointer that we aligned forward, and that's the pointer that you can operate on. So in the code that is calling it, as you can see here, I get back a pointer, I'll get back this result here from the allocator. That's now pointing to that first byte just after the allocation header that I created. I can fill that up with whatever I like. That's memory for me to use without causing any problems. And then I can resize, then I free. And very simply here, if it isn't a free, then I basically ignore it for this, or throw an error at this point. That's TBD whether I really need resizing. But then I really just do the reverse of what I did up in the alloc function. I take the pointer that you pass me, I would subtract the size of the allocation header, I verify that the cookie is what I expect it to be, i.e. it is actually pointing to a memory location that has been allocated by a call to alloc, and then I just free it. That's all I do. So that's very simple, and that gives me all of the functionality that I need to use Zig's allocator from standard library, which is great. All right, so now I have that. There's a couple of other things as well to do with Uefi's memory management. So you with the Uefi boot services, with the memory module or memory manager, there is a concept of memory map, and the memory map is the map of every allocation or every memory region that is available to the system. Everything from reserved areas to memory that has been marked as bad and unusable to I/O, everything. And so a memory map is very important, and both for you to keep track of where things are and how things are working out, and especially when you are doing your own OS, you will take that memory map as a basis for how you're going to lay out your own memory map and your own heap, system heap, for example. But for now, I just need this memory map to be available, because when I call exit, which I do here, I need to pass in a memory map key. And the memory map key, I suspect under the hood, I haven't dug into this too deeply, but the way it works is that whenever you allocate something, the memory map changes, of course. And my suspicion is that whenever the memory map changes, it calculates a hash of that, and it uses that hash as the key, so that when you call things like exit boot services, it can check, is the memory map that you have up to date with the latest memory map. If it isn't, that could be a condition and it will fail. It will not allow you to exit boot services, for example, unless you have the latest and greatest memory map. So I've added this functionality in here to get the memory map, so that I can use that very easily by calling memory map, as you can see here, memory map refresh. Not sure whether it's the best sort of implementation / API idea, but it works for this. And it's again, you sort of start learning how different languages have different ways of approaching problems, and they have different solutions to it. In C++, you might do it similar. You might have a little helper class that you can use, and perhaps you would overload an operator so that whenever you access it, it will double check if the memory map is fresh, is up to date. It will do the operations under the hood to refresh it if it needs to. I'm just sort of wrapping my head around how some of these ways of thinking apply to Zig. Now, the only thing that's interesting about this, I suppose, is that the get memory map function in boot services, you call it twice here. The APIs, the Uefi pre-boot and the Uefi services APIs are partly, or were in part, designed by Microsoft, and you can tell. So the cliche from the Win32 APIs that I'm sure many of you are familiar with, which is the calling in to, let's say, get some sort of resource or information about, your, I don't know, monitor, something like monitors, for example. Get me a list of all the monitors, enumerate devices, that sort of thing. The classic cliche is that you call it first with a buffer size of 0. It comes back saying that's not enough. This is how much I need. And then you call it again with the correct buffer size. And the same API mechanism is something you find in all the Uefi functions as well, that return any sort of variable list or variable amount of data. So we call it first with a memory map size of 0. It will fail. It will have adjusted the memory map size to what it needs to be. We up adjust it a little bit, and the reason why we do that is because we're now going to allocate memory, which changes the memory map. So we need to have a little bit of room in our memory map buffer for that change. And the industrial standard and recommendation is just add 2 times the descriptor size. You'll be safe. It probably could only be 1, but better safe than sorry. So we allocate the pool that we need, allocate the memory we need for the actual memory map, and then we get the memory map again proper. And now we have an updated memory map, and we have an updated memory map key. Okay, so down here what I've done, somewhat inspired by, I think it's in heap, yes, here in the page allocator, somewhat inspired by this sort of cliche here of having a global object or a global pointer to a particular implementation. So selecting the implementation based on, in this case, whether it's WASM or not, and then having that as a globally accessible pointer. Same kind of cliche here, memory map, which is globally accessible, points to this map state instance, which may or may not change depending on the type of runtime environment we're in. And that's the one we use when we actually allocate. So you can see here that we get the allocator. Actually, that is, there we go. Yeah, memory map. Refresh. So that's the one, that's the global instance of, if you like, of the memory map. And it's fine to have a global instance of this because there is only one memory map. We wouldn't have multiple of them or multiple instances of them. Okay, so we have an init function which I'm calling inside of the main function here as well, which is the kernel memory init. Kernel memory init does the first getting of the memory map, which we need, and then it just loops over the memory map and looks for conventional memory, which is effectively available and free memory. There are, let's see, I think there are about 10 or 12 different types, but we're only interested in the conventional memory bits, and we just sum it up. At the moment, I'm not using that for anything, but you would use that if you were going to create a more in-depth allocator of your own, and you could keep this memory from between calls to, this memory can be used and persisted across to the, after you've exited the boot, the pre-boot state. So I just print out a little bit of information about that, and we're done. Okay, so that's really it. That's the allocator, and just to run it again, see that everything works. So you can see here from that initialization, the memory map contains 21 entries. That will contain things like the boot code, so that's basically the firmware zone code, the boot code and boot data. It will contain our loader code, of course, our loader data, a number of reserved entries, potentially unusable memory, perhaps slightly less likely when running in an emulator. And then the conventional memory. And so we only count up the conventional memory. So even though in this case I've set up QEMU to give me 512 megabytes, what I get is 478 megabytes available for me to use. Again, remember, that's not because there has been so much memory allocated already, it's because a lot of that memory is used for other things, system memory, etc. But with the memory map, I have full access. I have access from the memory starting at 0 to memory all the way up to the top of, to the limit. Interestingly, just as a sort of mental, slight side note, but if you look at the memory map for Uefi, you will see that the first range, so 0 to a number of pages, might actually not be system memory. In the case of Tiano Core, which I'm running here, the memory map has a gap from 0 to, I can't remember exactly how high up, but fairly high up, which is where it has its own boot code and boot data, and then comes your loader. And that is perfectly sensible for Uefi, because with Uefi, we don't have a low megabyte BIOS memory range that is special, because that's what BIOS does, that's not what Uefi does. So it's quite an interesting one to do. In fact, if I had a look around, if you Google memory map for Uefi, you'll probably find that most of the hits are suggesting that there'll be a special range 0 to something, and then there'll be your code. And actually that's not necessarily true at all. So always useful to actually run these things and actually convince yourself, which is also why in my previous video I went through and did the checks for whether or not the machine state was what the standard supposes that it is. Again, not necessarily something that you need, but it's useful as an educational exercise, and it teaches you a lot of new things about both how to determine the state and what the actual state means. So always useful. And that's it for now. And I will move on. I think the next step is, as I was saying earlier, to dive into how I can debug this properly, because printf debugging, as much as I love it, it does get old and long in the tooth pretty quickly. So that will be the next step, I think. Thank you very much.